Okay, the next part of measuring the stars is going to be talking about their colours and how we assess them. So you may have noticed that I wrote down the magnitude with a subscript V. What is that MV meant to be? Well, the original magnitude scale is based on how the eye responds, and the eye doesn't receive light equally at all wavelengths. And our current magnitude scale is based on detecting visible light. And in fact, we narrow it down a little more than that. So MV is the visual magnitude. It's the magnitude as seen in visible light. It's actually slightly more carefully defined than that, and you'll see that as we move on. But it certainly does not account for wavelengths outside of the visible wavelength range. And so actually what we have is that we define these bands, and these bands are often defined to do with how you make a filter. So you can think of it as being, I've got a filter that lets in light that's a visible wavelength, but it's not all visible light. It lets in most light at around green-blue. It lets in a lot less light in yellow, and basically no red. It also doesn't let in much in the way of violet and indigo. So you've got some blue and some green and some yellow. And this is the definition of V. So that subscript V is really how bright is it in these wavelengths, and it's even weighted according to having the most at this wavelength and the least at this wavelength. We also have other filters called, so V is for visual, B is for blue, even though it's actually peaking in the violet, and it's giving you some ultraviolet down here, and it's even giving you a tiny bit of green down here, but no yellow or red. And here we've got an ultraviolet band that has a tiny bit of visible, but is mostly ultraviolet. And so, you know, basically different filters will let in different light, but also different detectors will behave differently. So the eye is sensitive to all of these wavelengths, but actually it peaks somewhere around here. It peaks in green as to its sensitivity, and it's less sensitive to blue and red. Whereas you might be able to tweak a photographic plate according to the chemistry, or a CCD is kind of like the chips that you have in a camera phone, where you're sensitive to light. You can tweak them to make them sensitive to the infrared or the ultraviolet, whatever. But so that we know what we're talking about, we define bands, that is, these filters that we're looking in. And so UBV are ultraviolet, blue, and visual, and those are things that can be done from the ground. You can see through the atmosphere at those wavelengths, and they're based on the standard set of filters. Actually, there are, you want to know exactly which one of these filters was used. We also have other filters, R for red, I for infrared, the JHK are also infrared, L and M are mid-infrared, and so on. We'll actually have a look at these. So here we can see, so this is also another version of ultraviolet, slightly different. So it's the prime, G is green, R is red, I is infrared, and Z is kind of a mid-infrared. And the primes actually are because they're not quite the same as ones that are also called R, I, and Z. Here you can see this is Z, and it's slightly different to this one. It's centered around the same wavelength, but it's slightly different. Then we have J centered at about 1.3, H centered at about 1.6, and K at about 2.2 microns. And these are partly to do with the materials we can make, and partly to do with the opacity of the atmosphere. And so here I've got, this is just giving you the central wavelengths, but they also cover large, there's overlap between them. So we have ultraviolet blue, visual, and then these are all infrared, but with increasing wavelengths. And so what we want to be able to do then is to be able to extrapolate from what measurements we do make in those bands to some sort of measure of how bright things really are. So we're measuring something in a specific filter, but the brightness will depend on the wavelength, and the brightness depends on the temperature too. So if we measure the brightness at some wavelength lambda, then its brightness is L sub lambda. But what we really want is the total apparent brightness, which is the apparent bolometric luminosity. So bolometric is just where we want it for all wavelengths. So basically we have to integrate this over the entire wavelength range from 0 to infinity, where we have some way of knowing how the light depends on wavelengths from 0 to infinity. This is pretty tricky, actually. And we know we can use the same sort of equations that we've already looked at for converting from luminosities or measured brightness to magnitude and vice versa. So if we've got the L-bol, we can work out mbol, which is the bolometric magnitude. And so what we need to do is to be able to get this L-bol, and if you've got some filter or other, this is going to affect what passes through. So a standard filter will depend on the brightness at a wavelength, so the brightness in a certain filter, brightness at a certain wavelength, and its bandpass. Remember, V was peaking in green. This is basically how that changes with wavelength. And so this is, and in some cases it's also has folded into it the sensitivity of your detector, because our eyes, we don't need to put a filter in front of them, they still don't receive light equally at all wavelengths. So it's a mixture of what light are we letting in and how sensitive are we to that light. And so what we actually do is apply what's called a bolometric correction. Why is it so hard to actually measure a bolometric magnitude? Well, it's impossible to do observations at all wavelengths from the ground. Satellites make it easier, but that's still, it's fairly new technology, and it's still, there's a lot of things in the sky. What are you going to spend your time on? And so what we want to do is to say, well, we've got this sort of object. If it's this bright at V and this bright at B and this bright at I, well, we can be fairly sure that we can come up with a function that fits over all wavelengths and be able to integrate. And so we can actually come up with a correction from a visual magnitude to a bolometric magnitude, but it does depend on the temperature of the object. And that brings us to the idea of color index. So a color index is basically, you've got two different measurements. So let's say we take a measurement in V and a measurement in B. The difference between the magnitude in V and the magnitude in B is a measure of the color. And so we're basically just subtracting one from the other. So the color index is the blue minus the visual. And it doesn't matter whether you're talking about the apparent or the absolute. We always subtract the longer wavelength from the shorter wavelength, so it's always B minus V. It would be V minus I minus R, and so on. It doesn't depend on distance. Because we're subtracting them, we're effectively getting rid of the distance factor. Any effective distance affects both the measurements. So if we think about here, I've got a star. It behaves kind of like a black body, right? And so I've got something that's at 10,000 Kelvin. It's emitting a lot of light in the blue, not so much in the red. So in my blue filter, it's going to be brighter. That means it's going to be more negative. In the V filter, it's going to be less bright. V filter's down here. It's going to be less bright, and so it's going to be a higher positive number, and so you end up with a negative B minus V. B is more negative, V is less negative or more positive, B minus V is positive. If you go to something cool like a 3000 Kelvin star, now we've got more red than blue light. So it looks reddish, and what we're going to get is that this will be more positive, this will be more negative, and so as we subtract a negative number, we get something that is positive. And then if we have something that's kind of, middling, like the sun, around something that's yellowish, then actually you have about the same blue and red, and so you're going to end up with something that ends up being close to 0 in its color index. Now this assumes that the color is an intrinsic property of the star, but that's not necessarily the case. There's a couple of things that happen. If you've got dust between you and the star, or even lots of gas, it will redden the starlight. This happens for the same reason that the sky is blue. When sunlight hits the atmosphere, it gets scattered by the particles in the atmosphere, and it gets scattered all around. The red light goes straight on, and the blue light keeps being scattered around. Well, the same thing happens with starlight hitting dust and starlight hitting the atmosphere. And so we get what's called reddening, so the sun looks reddest at sunset, that's because it's passing through more atmosphere. Stars look reddest at sunset for the same reason. And it's a wavelength dependent thing, and so it will affect the color index. And so you can't necessarily use just one color index to determine the temperature of a star, because it may be affected by these other factors. we also have something called color excess, which is, so we've got some idea that the color of the star is what we think it should be, and then we measure another color index, then the color index will be off. So basically we've got an intrinsic color for the star, and we've got more brightness in some color. That is called a color excess. And so we actually need to use 3 colors, that is 3 filters, which will give us 2 color indices. So let's say we've got UBV, we can do U minus B and B minus V, and with those 2 you can actually get the intrinsic temperature, because now you've got 2 points to anchor your black body curve, basically. And that will give you an intrinsic color, and it will tell you if there is an excess, and that excess is usually due to dust around the star or between you and the star. We can account for any reddening that happens because of the atmosphere, because we understand the atmosphere fairly well, but the other stuff which is either between us and the star as interstellar, or close to the star, which is circumstellar around the star, and that's the stuff that we may not be able to fix very easily. And so we can develop the idea of extinction corrections, that is, that we have this reddening, we can correct for the atmosphere, but we can also correct for interstellar dust, and the dust and molecules are basically removing light. They're taking light and making it so that it doesn't get to us. So dust in the way will absorb some light, and then it will emit it in the infrared, but if we're looking in V band, or B or U, we don't see that light at all, and so it looks like it's been extinguished, and so the light is said to have suffered extinction. And so when we measure the brightness of something, the magnitude in the visible, it will be affected. It will be fainter than it should be, and we have to account for this. And so the way that we account for it is we say that a star suffers from some sort of extinction A, and it will be with respect to whatever band you're looking at. So if you're looking in the visual band, it's AV, and the blue band, it's AB, and so on. And it's related to the amount of material it has to pass through. So the optical depth, and we talked about optical depth with respect to the sun. Well, we have optical depth of a cloud of molecules or a cloud of dust between us and the star, and it will be wavelength dependent, just like it is for the atmosphere and just like it is for the sun. And so now we can apply this, though, and say that instead of just having the distance give rise to m minus m, so the difference between the apparent and absolute magnitude is not just distance, it's distance and whatever extinction is going on due to things like dust and molecules. For some objects you don't need to worry about this, and for some you really do. And that's where we're going to stop for this segment.